We want to construct an open box. So we have an open box with a square base, and it's required to have a volume of 10 cubic feet. Here I've drawn a box, and so it's open, so it doesn't have a top part, and the volume is equal to 10 cubic feet. We want to express the amount A of material used to make such a box as a function of the length x of a side of the square base. Okay, so first off, we're going to have a length x of a side of a square base. So here's the base. The base of the box is right here. And we want this side and this side, because it's a square base, the lengths of all the sides are equal. So this length we're going to call x, and this will also be x. And a box also has a height, so I'm going to just let h stand for height. Okay, so we want to express the amount A of material used to make a box. So the amount of material used is the surface area of all of the sides of the box. So in other words, the area is going to be equal to, we're going to find the area of each side of the box without including the top because it's an open box. So notice that we're going to have, well, for the bottom, to find the area of the bottom, that's going to be x squared. Because it's a rectangle, so it's just the base times the height here of this square. So x times x. And then we're going to have, let me erase these lines so we can see it clearly. You see this side here. The area of this side is x times h, but also right here, this side, because this length is also h, is x times h, so we actually have 2xh. I'm going to erase that. So we also have the front side, which is x times h. But not only do we have the front, we have this back here. So let me erase this piece. You can see that back here, I have a side of the box, and this length is going to be x, and this is h, so we're going to have 2xh. Okay, so the area of such a box is x squared plus 2xh plus 2xh, and we are not including the top. Now we want to take this area function, so the amount of material used, which is this area, and we want to express it as a function of just the length x. So all of these h's here, we want to get rid of them. We only want to have x's in our equation. How can we do that? Well, we need to figure out how to write h in terms of x. Let's go with this piece here. We know that the volume of such a box is 10 feet cubed. So what is the volume formula for a box? Well, the volume is equal to the length times the width times the height. So it's going to be x times h. So x times h, which is x squared times h. And we know that this volume is equal to 10. Well, we can solve for h just by dividing by x squared. So h is equal to 10 over x squared. And now we can take this h and plug it into this formula, and we'll get rid of all of the h's. So now the area is going to be x squared plus 2x 10 over x squared plus 2x 10 over x squared. You can add these two together to get 4xh if you want to. it doesn't matter, we're going to get the same answer in the end. Notice that I have an x here and two x's here, so we can cross that out and leave one on the bottom. So the area is x squared plus, this will be 20 over x plus 20 over x. And if we simplify this, this is going to be x squared plus 220 over x, which is 40 over x. So this formula is the surface area, which is the amount of material that you would have to use to make such a box. Okay, so this is what we're going to call A of x. So instead of writing area here, I'm going to say A of x, where A stands for area and x is the variable we're using. Now let's go back to, since we've done part A, let's look at part B. How much material is required for a base that's 1 foot by 1 foot? This is telling us the length of the sides. The base is a square base, and x is going to be equal to 1. At the same time, for part C, it says how much material is required for a base that's 2 feet by 2 feet. For this part, we're going to let x be equal to 2. So all we need to do to figure out B and C is plug it into this formula. For part B, we want to figure out A of 1, which is 1 squared plus 40 over 1, which is just going to be 41. So we would need 41 feet squared, because area is always measured in, well, the units squared, and the units here happen to be feet. Notice that we're dealing with feet here. And then for a base that is 2 feet by 2 feet, so for part C, we're going to plug in 2 into our area formula, which is 2 squared plus 40 over 2, which is 4 plus 20, which is 24 feet squared. Notice that the larger the base, the smaller the area, at least for this particular example. When we went from a 1 by 1 base to a 2 by 2 base, the area of the surface area is 24 feet for 2 by 2 and 41 feet for a 1 by 1. Part D says use a graphing utility to graph this function A, and for what value of x is A the smallest. Okay, so here is the function, and let's graph it. So A is equal to x squared plus, I believe it was 40 over x. And I'm going to zoom out some. Okay. So let's talk about the domain a little bit. Notice that if we zoom out a lot, we get this very strange graph. It's really actually hard to interpret like this. Let's zoom in a little bit. First off, the domain. What can we plug in for x? Obviously x can't be 0 because we have a problem here, but we're also dealing with sides of a box, which tells me that x has to be greater than or equal to 0. So here's 0. So I'm going to ignore anything for this function that's on the left of 0 because it doesn't deal with a box. We can't have negative lengths. So remember, we're trying to find the value of x. That's the smallest, right? Let's look back at the problem. For what value of x is A the smallest? Now A is your y values in this picture. You can see that your y values, when you get close to 0, your y values are really big. But as you go away from 0, so you're going this way on the x-axis, you can see that your y values are going down until you get to here. And it looks like this is the lowest point on your graph, at least on this portion over here. Not over here, but we're ignoring this because it's not going to be in our domain. So the lowest point is when x is 2.714. Let's write that down. So when X is 2.714, A is going to be the smallest, and the value of A is going to be 22.104. So A is going to be 22.104. What does this mean? And why would we even want to find something like this? So notice when we had a 1 by 1 box, we got the area was 41. When we did 2 by 2, it got a little bit smaller. What we're saying is the smallest area, surface area, so the amount of material you're going to need is when you plug in this value 2.714. And what you're going to get is 22.104. So any number other than this one, so let's say you plug in 3, you're going to get a bigger area. And any number smaller than this, like 1, you're going to get, as you saw, a bigger area. Now, why would you want us to find the smallest area? So let's think about if we were actually producing boxes. So that was our job. We had some company where we wanted to make boxes. Well, if you make a box, you want to use the fewest amount of materials to make the box, because you want to make it cheaply, and you want the box to hold as much stuff as possible. So if we have a box like this where we want the box to have a square base and we want it to have a specific volume, so we want the box to hold 10 feet cubed of material. And so this is, let's say we got an order from a company that says, hey, can you build a box that holds 10 feet cubed of material? And you're like, sure, we'll make you the box, but we want to do it as cheaply as possible so we can maximize profit, right? So what we're going to do is we're going to find the minimum of this area function, because this is going to tell us how much surface area we're going to need for that box, and you want to use as little material as you can to make this box. And so that's what you're doing here. You're finding the length of X, the length of this square box, that will give you this volume, but it will minimize the amount of material, which means minimize the cost for you.